to the University of Texas at Austin. This is the Real-Time Digital Signal Processing Laboratory course for the spring 2014 semester. I'm Professor Brian Evans. This is Lecture 5, Part 5. Lecture 5 is on finite impulse response filters. So far we've covered quite a few things. We've covered many roles for filters. This is spectral estimation, spectral analysis, and spectral shaping. We talked about convolution. This is how filters work in the time domain. The output in the time domain is the convolution of the input signal in the time domain and the impulse response of the filter. We've talked about Z-transforms, which give us another analysis tool to analyze the function or properties of a linear time invariant system. The Z-transform of the impulse response is the transfer function. This allows us to know what happens in a generalized transform domain from the input of the filter to the output of the filter. Talked about frequency responses of LTI systems, and certainly a good example of this is for filters. That is to say, in this class, a filter is a bounded input, bounded output, stable, linear time invariant system. We talked briefly about filter design. I gave a demonstration using the filter design and analysis tool, or FDA tool, in MATLAB. So today we're going to go into a demonstration of applying FIR filters to images and look at what happens when we cascade them. So let me jump ahead a few slides. For the demonstration, we're going to need two filters. We're going to apply two filters to an image. One is an averaging filter, and the second is a first-order difference. So here is a review that we covered in Lecture 5, Part 3 at the end. And this is the simplest case of a two-tap averaging filter. In the two-tap averaging filter, the input-output relationship is as follows. The output y of n is simply the average of the current input value and the previous input value. We can find the impulse response, and again, the impulse response uniquely characterizes a linear time invariant filter. This filter is linear and time invariant if the initial condition is 0. The initial condition is the memory of the previous input value. So assuming that the initial condition has to be 0, then it's LTI. The impulse response can be obtained by letting simply little x of n be equal to the impulse in discrete time. And the resulting impulse response is simply 1/2 of the discrete time impulse plus 1/2 of a delayed discrete time impulse, and that's plotted to the right here. So the impulse response has a value of 1/2 at the origin and value 1/2 at index n equals 1, and otherwise the amplitude is 0. We can then obtain the frequency response just to know what frequencies pass through the filter and which ones do not. By applying first the Z-transform, we can take the Z-transform to find the transfer function. We can do this by taking the Z-transform of the impulse response. That Z-transform is simply 1/2 plus z to the minus 1 times 1/2. Or if I can write this probably in a little more familiar way, 1/2 plus 1/2 times z to the minus 1. We can then obtain the frequency response by taking the Z-transform and substituting z equals e to the j omega. From the frequency response, we can factor it to find a magnitude and phase form. And the way to do this is to factor out the delay corresponding to the midpoint of the impulse response. So the midpoint of the impulse response is here at n equals 1/2, which is not on the integer grid, but nonetheless is the midpoint. So the midpoint is at n equal 1/2. Now again, this should concern you a little bit. It still concerns me that the midpoint is not on the integer grid, but nonetheless it is the case. So we factor out the phase shift corresponding to the time shift of 1/2 sample. This gives us two terms that are conjugate symmetric or conjugates of each other. And the conjugate, so if I pull out e to the minus j omega over 2, I get e to the plus j omega over 2 plus e to the minus j omega over 2. This term on the right simplifies to 2 times cosine omega over 2, and the 2 1/2 gives us 1. So these two together give us the cosine omega over 2 term, and then what's left is e to the minus j omega over 2. So we're left with an amplitude function that's really a magnitude. So this form is a magnitude and phase. Now the magnitude response is a low-pass response, but it's not the world's best low-pass filter. The low-pass response looks something like this. When omega is 0, I can plug that in. I get 1. When omega is pi, I get 0. And when omega is minus pi, I get 0. So here is the magnitude response sketched. Again, not the world's greatest filter. Oops. But nonetheless, it's a low-pass filter. So again, the value of 1 at the origin and 0 at omega equal pi and omega equal minus pi. Now, a couple of things for the demonstration that we'll need. One is that the averaging filter is low-pass. Second is that there's a delay through this filter, and that delay, in the worst case, you can look at the block diagram. This is the tap delay line for the two-tap averaging filter. Again, coefficients of 1/2 for h of 0 and 1/2 for h of 1. In this tap delay line block diagram, the worst case delay is 1 sample. But it turns out, because of the symmetry in the impulse response, the actual delay through the filter is 1/2. And you can see that by looking again at the phase response. The phase response looks like the phase for an ideal delay of 1/2 sample. Now in practice, when we convolve or apply this filter to an input signal, we're going to convolve the impulse response h of n with the input signal x. When we do that, the result of x of n, if x of n is finite in duration, we'll get a wider result. So when applying this filter, the result of y will be the length of x if it's finite, plus the length of h, which is 2, minus 1. So the output y of n will be 1 sample longer than the input x of n, provided the input x of n is finite length. We'll need this a little bit later in the demo. The second filter we're going to work with is the first order difference. First order difference has very similar analysis as in the previous slide, has the same form as a tap delay line or block diagram. Its worst case delay is 1 sample, and its real delay is a 1/2 sample, just like it is in the two-tap averaging filter case. So again, the input-output relationship, this is a normalized difference equation, and it has a very similar form. The only difference is the plus sign that was here for the two-tap averaging filter has become a minus sign. Otherwise, the analysis follows in exactly the same way. Impulse response is shown here. I have a value of 1/2 at the origin, value of 1/2 at n equals 1. Otherwise, the amplitudes are 0. Again, a value of 1/2 at the origin, a value of minus 1/2 at n equals 1. We can factor out the phase shift corresponding to a 1/2 sample delay, just like we did before, and we get now a difference of 2 conjugate terms, and that simplifies to 2j sine omega over 2. The 2 and the 1/2 give us 1, and so the simplification of these two terms gives us sine omega over 2 times j. Now there's a interesting story here. So the j can be written as e to the j pi over 2, which you see here. This gets us in the same phase representation as the linear phase term. And so we end up with an amplitude function, sine of omega over 2, and a phase term, which is a line, but it does not go through the origin. It goes, when omega is 0, the phase is pi over 2. But nonetheless, the group delay, which we defined before as a derivative of the phase function, has slope minus 1/2 over all frequencies. So it looks like a delay of 1/2 sample through the filter in terms of its phase characteristics. The amplitude is a sine, and so if we were to plot the magnitude response as a function of frequency, it would be a sine wave, and then we take the absolute value of that. So again, from a sine of pi over 2, to be more precise. So this is a sine term, has 0 at the origin. And again, it would be a sine normally, but that sine, in terms of absolute value, will kick up to be non-negative. So we get this kind of shape in the magnitude response. Again, we'll need this for the demonstration. So this is, you could say this is a notch filter. It removes 0 frequency, which it does. You could also say it's a high-pass filter, or even a bandstop filter around 0. To me, the best description of this is high-pass as a filter, although it's not, again, the world's best high-pass filter. Okay, so let's go on to the demo. And in the demonstration, we're going to apply 2 filters. Again, the averaging filter, but in this case, it will be 5 coefficients, and then the first-order difference. The averaging filter in the longer version of this has the same characteristics. This will be a low-pass filter. So we're going to take, again, this 5-tap discrete time averaging FIR filter with input x of n and output y of n. All we're going to do is simply take the average of the current input value and the previous 1, 2, 3, 4 input values. Normally we would divide by 5 to get an average. In this case, we simply multiply by 5, and now all the coefficients become the simpler one, more easy to implement. The shape of the frequency response does not change, but its value does. It scales by 5. This is a low-pass filter, and we'll see that in image processing, this corresponds to a smoothing or blurring of the image. We'll see this visually in just a second. And the impulse response is just 1, 1, 1, 1, 1. Otherwise, it's 0. Now, in terms of magnitude response, we can go through the same procedure. Find the impulse response, take the Z transform, convert the Z transform into a frequency response. And what we'll see in doing all of that is we'll get a magnitude response that has 4 zeros. In other words, this Z transform will have terms that equal to 1, z to the minus 1, z to the minus 2, z to the minus 3, z to the minus 4. So the actual transfer function is simply a sum of negative powers of z up to z to the minus 4th. So we're going to have 4 roots of this transfer function, or 4 zeros. Those zeros will be on the unit circle. And in the frequency response, this is going to correspond to 2 frequencies being removed or zeroed out. And then the value at the origin is going to be equal to 5. Again, in the Z domain, so again, to convert from the Z domain to the Fourier domain, we take the Z transform and substitute Z equals e to the j omega. So at omega 0, this corresponds to Z equals 1. So a way we can read off the DC response of this filter is simply let Z equals 1. So omega equals 0 implies Z equals 1. So in the Z plane, the value Z equals 1 is the 0 frequency point. Again, that value will be 5 if we let Z equals 1 and plug that into the transfer function. Another thing to notice about the averaging filter is that the first null bandwidth, or the first null value here, is actually more generally 2 pi over n, where n is the length of the filter. So this tells me that if I want to quickly design a filter that's low pass with a certain bandwidth, then I can simply use an averaging filter of the right length to achieve that. Now the bad news is that the stop band attenuation the distance from pass band to stop band is unfortunately a constant, 13.5 dB, and this does not change with the length of the filter. So it's not the world's greatest low-pass filter, but nonetheless, it's a low-pass filter. For the first order difference, we've already analyzed that on the previous slide. We're going to use the version that's, you can say, unnormalized. And that is to say the DC component here is going to be, it's still zeroed out, but the value, excuse me, of pi and minus pi is going to be 2. So this is going to be a high-pass filter, and it's going to, in the context of images, it's going to sharpen the input signal to some extent, but we'll see what it really does. It will extract edges and texture. The impulse response is shown before, although it's scaled by 2. It's 1 at the origin and minus 1 at n equals 1. All right, so let's proceed with the demonstration. All right, this is a demonstration from DSP first. This is from DSP first by McClellan, Schaefer, and Yoder. And I'll go right, this is right off a web demo that I'll run outside of PowerPoint. In the demo, we're going to have the original image filtered by the, first filtered by the two-tap averaging filter, and then we're going to apply the first order difference. So first we get a blurred image from the averaging filter, and then we apply the first order difference to get a sharpened version of that blurred image. Also, we'll take the original image, apply the first order difference to get a sharpened image, and then we'll apply the averaging filter to blur it. And the question is, will we get the same answer? Okay, so let's see. So here is the mandrel demo, the mandrel image. This image is a matrix, and you can kind of see the dimensions here. It's 256 by 256. Each entry is an 8-bit unsigned value of the level of gray from 0 to 255. For the purposes of display, or in general, the 0 is the background intensity and 255 is the opposite of that. So in the case of display, 0 is black and 255 is white. In the context of printing onto white paper, the opposite is true. 0 is white and 255 is black. So it simply depends on context. So in this context, 0 is black and 255 is white. So again, we have a matrix, 256 by 256, and each entry is the gray level at that point in space. It is an 8-bit unsigned value, again, taking values from 0 to 255 inclusive. If we cut along the mandrel's image here, let's say along row 100, and we follow the mouse, what we see is a lot of alternation between white and black, black and white. Any transition from white to black is the highest, is the most significant possible change in the spatial domain, and that corresponds to high frequency. If we alternate between min, max, min, max, min, max, that's the highest frequency possible. This would be equal to half the sampling rate. As we go across the image, we'll see that in the nose and cheek area, we have a white area that is, we can see a black line followed by white, black line followed by white. Again, any transition from white to black is a high frequency transition, and also black to white as well. So what we see here in an image is that the high frequency content is representing both texture of the hair and lines in the face. So if we apply a low-pass filter, those features should blur out, and we'll see that they do. So the first step is to apply the averaging filter. The averaging filter is a 5-coefficient filter. It has, it's unnormalized. The DC value is 5. I have 4 zero locations, so I have 2 positive frequencies that get eliminated, and 2 negative frequencies that are the negatives of the positive frequencies being eliminated. So I have 2 frequencies being removed completely by the filter, and we cannot recover them once they're removed. If we look at the phase response, we're expecting a phase that is a line and this phase is a line except at these points of discontinuity. These points of discontinuity line up exactly with the zero locations in the magnitude response. So these frequencies at which the discontinuities occur do not pass through the filter. Why the discontinuities occur is the following. The frequency response, or the Fourier transform of the impulse response here, which is a rectangular pulse in the time domain, is something that looks like a sink. The sink would normally follow my mouse here, and since it's a magnitude response, we take the absolute value, so the negative component, or the negative part, kicks up to be non-negative or positive, except for the two zeros. This sign change around the zero crossing corresponds to these discontinuities of pi in the phase response. However, if we apply the definition of group delay as the derivative of the phase function, then except for the 4 points of discontinuity, this slope is constant and has the same value over all frequencies, again excluding the 4 points of discontinuity. We can estimate the slope by looking at change in y over change of x. Here's a change of x that's 1, and a change of y that's -2. So the slope we can estimate to be -2. This means that the group delay through an averaging filter of 5 coefficients is 2 samples. Now, the way that we're going to go about applying this one-dimensional filter to a two-dimensional image is as follows. I'm going to first take the 1D filter, and along each row, I'm going to apply it to create an intermediate result. And in the intermediate result, I'm going to apply the filter down each column to produce the final version of the 2D filtered image. Now, as a result of applying this 5-tap filter to a row that's 256 entries long, or samples long, my result is going to be 256 plus 5 minus 1, or 261 samples. So after applying this 5-tap averaging filter to the mandrel image, I will, as I do it along the rows and then subsequently down the columns, I will get a new image that's bigger than the original mandrel. The new image will be 261 by 261. This will become important later, because later we're going to display this back into 256 by 256, and we have to figure out a way to convert this larger 261 by 261 image back to 256 by 256. So one thing we can do is simply throw away 5 rows and 5 columns. The question is, which 5 rows and which 5 columns? So the easiest thing to do is to throw out the first 5 rows and the first 5 columns of the resulting image after filtering, simply because a filter takes time to respond to the input, and the response here is complete after 2 samples or more. The group delay is 2 samples. So if I throw away the first two rows, first 2 columns, and the last 3 rows and the last 3 columns, that would work. Or if I throw away the first 5 rows and the first 5 columns, that also will work. All right, so let's get on. And again, here's the impulse response of the 5-tap averaging filter. All right, so let's apply this to the mandrel image, and we get a blurred version of the mandrel image. And so the features here are blurred out, the lines and the texture get blurred out. That is to say, we are passing low frequencies, which correspond to relatively constant areas of intensity, and we are attenuating, because they fall in the stop band, the frequencies that correspond to texture and lines, or edges, in the image. If we then take the result of the 5-tap averaging filter and apply it to, and then apply the first order difference, I get what looks to be an interesting effect. What I've done is it's a way to extract edges from the image, and you'll see that I pick up the texture in the hair now looks like a bunch of lines, and the lines in the face are also pulled out of this. So this is a way to do edge detection in an image, and it's a very common way to do it. So in image processing today, a very common way is to take an image, apply a low-pass filter, then apply a high-pass filter for the final step in the edge detection. A very common edge detector in image processing today is called Laplace Gaussian, where you apply a Gaussian filter first, which is a second order, which is a averaging filter, and then following the Gaussian filter, Gaussian means the shape of the impulse response is Gaussian, and also the shape of the frequency, the magnitude response is Gaussian. I then apply the Laplacian, which is a second derivative, to extract edges. It's a very common edge detector today in image processing. All right, so back to our, let's go back to our original mandrel. All right, so the one insight is how to apply filters to images, and what does that mean? The second insight is that in signals and systems, we were taught that a cascade of two linear time invariant systems can always be switched, and the resulting calculation will be unchanged. That is a correct statement from theory. When you go to implement this, it takes a little bit more, you have to add a little bit to that to make it work when you implement. So let's talk about that. So here's the other way of doing the filtering. We apply the first order difference, then the averaging filter. So let's look at the result of the first order difference. It's kind of edge detection, a bit noisy, I suppose, but it is a kind of edge detection. If we then apply to this low-pass filtered image, the high-pass filtered image, we now apply a averaging filter, we get a blurred version of what you see on the left. Okay. Now the question now is this the same image as I obtained from filtering first by the averaging filter and then applying the first order difference? And the answer should be yes, and there may be slight differences in your viewing of this, but these two should be bit for bit identical. There's no reason why not. Now what you'll also notice in the comparison as you're looking over this is that the image now has been brought back to 256 by 256. The result of applying the averaging filter gives us a bigger image that's 261 by 261. If we apply the first order difference to that, the size of that image now becomes 262 by 262. And I have to crop back to 256 for comparison with the original input image, which I'll also do in a second. So again, I can throw out the first three rows, last three rows, first three columns, last three columns, because both filters have linear phase. Or I could throw away the first 6 columns and the first 6 rows of that final 262 by 262 result. Either way is fine. Okay, so these two should be bit for bit identical, and we'll talk about why that is when we get back to the slides. And last, we'll compare the mandrel with the original. We'll compare the original mandrel with the edge detected version, and you should see the edges line up very nicely with the original image. Okay, again, this is back to where we were, which is about slide 18 or 19. It was 19. So again, these are two filters that we applied to the image. And let's discuss the result that we had seen. Okay, so again, the result of this filtering is that we end up, if we apply the low-pass filter first, we get a blurred image. So if we apply the low-pass filter first, we get a blurred image, and then if we apply the first-order difference, we get a sharpened version of that blurred image. Conversely, if we apply the first-order difference filter first, we get a sharpened image. If we then apply the 5-tap averaging filter, we get a blurred version of the sharpened image. Now, these two types of filtering will be identical. That is to say, if we switch the order of the application of the two LTI filters, the end result will be the same when we implement, provided that that all the computations are performed in exact precision. This means that we cannot lose any bits in the arithmetic that's involved. So as we filter, we're going to add a bunch of numbers together for both the first order difference and the 5-tap averaging filter. The number of bits that we need whenever we add two numbers together is one more bit than we started with. So if we add two 8-bit numbers together, worst case we need 9 bits. So for the first order difference filter, we're going to need a 9-bit value to store the intermediate result by filtering along the rows. We'll then filter that 9-bit image along the columns. We'll need a 10-bit value to store exactly the computations. For the averaging filter, it's a little more complicated. We're adding 5 numbers together to produce a particular output value. And so if I add two 8-bit numbers together, I'm going to need a 9-bit result. I mean 9 bits to store that result exactly. If I add two 8-bit numbers and two more 8-bit numbers, I'll need a 9-bit number for x of n minus 2 and x of n minus 3. I'll need a 9-bit number for x of n and x of n minus 1 being added together. If I add the two 9-bit numbers together, I need 10 bits, worst case. If I then add this 8-bit number, x of n minus 4, I'm going to need 11 bits, worst case. So I need 3 additional bits beyond what I started with. So when I apply this averaging filter along each row of the mandrel, I'm going to need 3 additional bits to store the results of that filtering without losing any precision. And then if I take that intermediate image and filter along the columns, I'll need another 3 bits to store the calculations exactly. So the application of the averaging filter along each row and then down each column, I'll need 6 additional bits. And then the first order difference along each row and down each column, I'll need 2 additional bits. So in the end, I need 8 additional bits from what I started with to get exact precision in the result. I started with 8-bit numbers. I'll need 16-bit numbers in the end without any loss of precision. So if I do all the calculations in this demonstration in 16 bits, I don't lose any information. I keep everything exactly. And in this demonstration, it is done in double precision floating point arithmetic because it's done in MATLAB, which has 53 bits of mantissa. We have way more precision than we need to store the intermediate and final results. So again, to kind of restate what we learned in signals and systems to be appropriate for implementation, the order of 2 LTI systems in Cascade can be switched under the assumption that computations are performed in exact precision. It also means that as I transmit results from one filter to another, for example, between the result here of so if I transmit the blurred image to the sharpening filter or the high-pass filter, no bits can be lost either in that communication. So I need to also have exact precision in the storage of these intermediate results as I pass them from one filter to another. So under the assumption that the computations are performed in exact precision, then if we switch the order of 2 LTI systems in Cascade, we get exactly the same result. They're equivalent. Okay, so just a slide here on what I basically just said on the adjusting what we know about cascading 2 LTI systems together. Okay, so that is the demonstration for this part of it. I'm going to now talk about the importance of linear phase and give another demonstration of how that's important. Okay, so linear phase, the importance of linear phase varies with the application. So for speech signals, it depends on the context. If it's speech compression, as in speaking on our smartphones or cell phones today, phase is removed. Phase is not that critical in a point-to-point communication. However, phase is useful when we want to locate a sound source. So if I walk around the room, if you were in the classroom, you could hear my voice and without seeing me, be able to locate me within 5 degrees of accuracy in the horizontal direction. In the vertical direction, our hearing is not as sensitive. Our accuracy is about 30 degrees in the vertical direction. And it kind of makes sense if you ever heard someone call your name from above you, maybe up 2 or 3 stories out of a balcony, you really have a hard time locating where they are. But horizontally, we have pretty good localization capabilities. Now, this localization capability in a human is fairly complicated. It's not just as simple as linear time invariant processing. But but the phase difference does matter. It helps our ears locate sound sources. Most of that location, however, does reside in the middle ear, and it's very much nonlinear and very sophisticated. But so where phase does matter is locating sound sources. And if we were to try to automate this, we can automate locating a sound source by having a pair of microphones, or more than 2, and using the time difference of arrival to figure out what angle the sound came from. Linear phase is also crucial in images, and I'll explain that on the next demo. It's also critical in many, but not all, communication systems, and we'll see that throughout the class. In audio, it's a little more complicated. If it's single-channel audio, we are certainly sensitive to some amount, if it's a large amount of deviation from linear phase. But if it's 2 channels or more, our ears are, or we hear with both, it's amazing what our ears can do to cancel the same distortion on 2 channels of audio. Our ears are very good at kind of canceling that out and can handle a little bit more deviation than with 1-channel audio. It's pretty interesting. Okay, so in audio, we certainly want to get filters that are close to linear phase, but we can tolerate some deviation from linear phase. To get linear phase, we've got to have FIR filters, and the FIR filters have to have special properties. That is, the impulse response has to be either symmetric or anti-symmetric about the midpoint. Otherwise, the FIR filter does not have linear phase. Any infinite impulse response filter, we haven't talked about those yet, but these involve recursive difference equations. Any infinite impulse response filter, that is to say with feedback, that I can build cannot achieve linear phase over all frequencies. Doesn't mean they aren't useful, it just means that they're limited in how close to linear their phase response can be. And again, depending on the application, this may be just fine. So let me give you a visual demonstration of images and why the phase matters. So here's an image that I've taken from MATLAB, and I'll show you the original in just a second. And I've done 3 things to that image. First, and this is to show the importance of linear phase. And for images, a lot of important visual information is in the phase. Yes, there's important information in the magnitude, absolutely. It's also a lot of important information in the phase. So let me show you an example. So I've taken an image, which I haven't shown you yet, and I've taken the fast Fourier transform, or the Fourier transform of the image. I've set the phase to 0 and kept the magnitude as it is, not changing the magnitude. And I took the inverse Fourier transform to get back to the time domain. So what I'm showing you here is the image content corresponding only to the magnitude response, or the magnitude content of the Fourier components of the image. Not very interesting. Constant. Not all that useful. Okay, the second case, I take the same thing, take the fast Fourier transform of the image, set the magnitude to 1, take the inverse FFT, but now I have a complex result. I have a complex valued image, and I plot the imaginary component. And there's at least something here. It looks, maybe there's a little bit, some noise in here, maybe there's a little bit of structure you can see in parts. Maybe some geometric shapes kind of show up, maybe not. Excuse me. But there's more than just a constant value. All right, third option, third approach here, a little more detail showing up. I take the FFT of the image, set the magnitude to 1 again, so I keep the phase information unchanged, take the inverse FFT, and I keep the real component of the result in the spatial domain, again, because the inverse FFT is complex valued, generally speaking. And now I probably see a little bit more detail. If you kind of look closely at what you're seeing, there's some squares and rectangles and some lines. Okay, so there's some shapes in here that we can now discern. And the original image is this. Okay, so the original image is an aerial view. This is an image in MATLAB, comes standard with MATLAB. And again, it's not to say that magnitude information isn't useful, because it is, but the phase is extremely useful. Okay, so again, so there's the original image of an aerial view of a city, or certainly an inhabited area by humans. Okay, so again, this is the, and again, so the magnitude has useful information, and so does the phase. So when processing an image, it's very important to have the phase response of your processing be sensitive to keeping the phase information. So linear phase is certainly one way to go about that. And many filtering operations in image processing, as far as convolution is concerned, in fact have linear phase. Okay, so for the last piece of this lecture, I want to talk a little bit about the last piece of finite impulse response filters is how do we go ahead and implement these efficiently in software, and then what computer architecture features can help that software run faster. And so for a finite impulse response filter, this means that the duration of the impulse response, h of n, is finite. That is to say, the extent is finite, which means that this impulse response has zero value in amplitude for some n outside of a finite interval. So m is some integer value. In the 2-tap averaging filter, it was 2. The 5-tap averaging filter, m was 5. So the time domain behavior of the filter is convolution. So I'm convolving the input signal x of n with the impulse response h of n. And I can do this two ways. Either I can hold, so I can either hold h of n in place and flip and slide x, or I can hold x in place and flip and slide h. In filtering, for FIR filters, we prefer to hold h in place and flip and slide x. This gives us the tap delay line block diagram representation for the FIR filter. So again, I have this. So to compute one output value y of n, I need to first, my summation becomes finite in extent because h of m is finite. So I don't have to sum from minus infinity to infinity. Instead, I can sum from 0 to capital M minus 1 inclusive. For every value of little m in this flip and slide convolution formula, I need to do one multiplication and one addition. So the complexity here is capital M multiplications and capital M minus 1 additions. So the capital M multiplications and capital M minus 1 additions. That is to say, an FIR filter has order M calculations. It's exactly M additions and M multiplications and capital M minus 1 additions. Now we can collapse this to capital M multiply accumulates. So we can say more compactly that a filter takes capital M multiply accumulate operations, and we'll call those max. So the output depends, so there's also some data management here, because the output depends on the current input value and the previous capital M minus 1 input values. We have to store those previous input values, and we have to do this efficiently. We have to do the storage and maintenance efficiently. The actual arithmetic, so we have to, in the summation, if we look at it another way, it's really a vector dot product. And that vector dot product, the dot product here involves two vectors, each of length capital M samples. The first vector is the vector that includes the current input value and the previous capital M minus 1 input values. The second vector is contains the values of the impulse response. Now, so this FIR filter amounts to a vector dot product and efficient memory management for the current and previous input values. And if you can do those two things fast, you have a very fast calculation and completion of the FIR filter for every input sample. So when a new input sample arrives X, we have to update this vector, and we can do this efficiently through circular buffering. So we're going to take the new value of X of n, put it into the circular buffer at the oldest location, so we get rid of the oldest value, put the newest one in, and keep track of where that newest point was entered. And that means that when we need to walk through the array for this summation calculation, we can start wherever it happens to fall in the circular buffer, and then move forward or backwards. I guess we move backwards in time according to the summation. So either we start at m equals 0 and count up to capital M minus 1, or we start at capital M minus 1 and count down. And the down counting is actually a little more common in an implementation. So we can start then with the oldest sample and work our way to the point of getting to the newest sample. So we can actually down count from capital M equals capital M minus 1, and then get all the way down to capital M, little m equals 0. So the question here is, what instruction set architecture features would you add to accelerate FIR filtering? And if you look at what we need to do fast, we can sort of take it one at a time. First, I need to get fast down counting. I need a fast down counter to go from capital M minus 1 to 0. For every value of that counter, I need to multiply two numbers together. I need to add that multiplication to the previous results that I've calculated. So I need to fast multiply, fast add. Fast down counting. I also need to manage a circular buffer efficiently, and I need to address into the circular buffer efficiently. So the circular buffer has finite length, so if I need to know where I'm at, I look at the value of little m. I know what little n is. I know what little m is. And so what I need to do now is find where in the circular buffer that corresponds to. So I can always take n minus m, and I can do modulo. So this calculation is actually n minus m modulo capital M. This tells me where I am in the circular buffer. The modulo here is, this is the C version of modulo. Right, so this is the modulo operation. So this modulo operation gives us the remainder of taking m minus m and dividing by capital M. It has a value from 0 to m minus 1 inclusive. So I need to be able to have in my addressing modes modulo indexing, because I'm going to need to use it every time I need to take a little value of m and compute the product. So again, just to summarize here, I also need fast on-chip memory to be able to get the data from on-chip memory. So X is stored in on-chip memory, local memory. I need to get that to the registers fast. I also need to read in the coefficient values, h of 0, h of 1, and so forth, fast. Okay. So if I kind of put that all together, what do I need? A fast down counter. I need fast multiplication, fast addition. I need fast local memory and a fast local bus. And if I look at what happens, I actually need to do, for every multiply, I need to do 2 reads at one time. So I also need 2 data buses. If I could have that, that'd be great. And I have that on the processor in lab. So in the 6748 in lab, the TIC 6748, I've got 2 data buses. I've got high-speed multiply, high-speed addition. I have a little bit of the on-chip memory. I have a little bit of delay getting from on-chip memory to registers, but I can pipeline that. And then I want to store the result, y of n, back to local on-chip memory. Again, I incur some delay doing that. The modulo addressing is part of the instruction set. It's part of one of the addressing modes, so that's no overhead. There's no delay to use modulo addressing on the C6000. And that's about, the down counting on the C6000 unfortunately has to be done in software. There's no hardware down counter on the processor. So we'll have to manually decrement by 1 and then loop if the counter's not 0. All right, so thank you very much for coming, and we'll see you next time.